In the last video, I showed you that normal distributions can be constructed to look just like binomial distributions as long as n is quite large and probability is quite close to a half. I'll talk in this video about exactly how large n needs to be and how close to 0.5 the probability needs to be. And I'm also going to show you how to actually use that normal distribution in order to find probabilities that approximate binomial probabilities. Let's have a look. So we've now seen that if you have a binomial distribution with n trials and probability p, then you can form a new distribution, a normal distribution, let's call it y, that looks really similar, where your mean is n times p and your variance is n times p times 1 minus p. How big does n need to be? Well, there's no hard and fast answer, because essentially the bigger the better. But as a rule of thumb, you want to say if n is bigger than 50, then you definitely should be using an approximation. How close to p? Again, it's the closer to 0.5, the better. But you might say it's something like if p is between 0.35 and 0.65, you should be fine. Now, in reality, in exam questions, they're pretty much always, in fact, I've never seen a case where they didn't do this, going to say something like, using a suitable approximation, find the probability of blah, 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 blah. And if they say using a suitable approximation, well, the only approximation that you're going to be learning about is normal approximations to binomial distributions. So it's going to tell you which approximation to use. So don't get too hung up on, oh, but what if n is 50 and what if p is 0.33? It's not going to happen. They're just going to tell you to use an approximation if they want you to. But for your own interest, the bigger n is the better. So if it's 50, that's fine. If it's 40, that's probably about fine as well. It depends how much you care about the accuracy of your answer. But in general, bigger than 50 and p somewhere between about 0.35 and 0.65 should be fine. All right, let's have a look at how we do this. So here is our distribution from before. And remember that we were able to make a normal distribution that looked just like it, or really similar to it, that had a mean of 60 times 0.45, which we saw was 27, and a variance of 60 times 0.45 times 0.55, and that one was 14.85. That's the variance there. So how could we use that to calculate the probability? Well, it'd be an estimate, a good estimate, of the probability that x is less than or equal to 20. Well, we can't just say work out the probability that y is less than or equal to 20. And the reason is that one of them is a discrete distribution and one of them is continuous. Imagine it like this. Imagine that you've got some of the bars of your binomial distribution like this. And let's say that this was bar 20 here, this was bar 19, this was bar 18, and this was bar 17. So, and so on. It would continue all the way down here. Well, if we were going to work out the probability that x is less than or equal to 20 using the binomial distribution, essentially what we're doing is we're taking all of that bar, plus all of this bar, plus all of this bar, plus all of this bar, and so on. The problem is, if you go ahead with your normal distribution, say I want everything that's less than or equal to 20, well, 20 sits right in the middle of this bar. Okay, 20 would chop it off there, and you would just be finding the area of everything to the left of that line. Because remember, normal is continuous, so there's a difference between 20 and 20.0, 0.05 and 20.3 and all of these things. So if we only had everything to the left of that line, we'd be missing half of that bar, all of that stuff there. So you have to, and let's just kind of zoom in, recognize that the 20 bar on the binomial distribution, 20 sits in the middle of it, which means it occupies all of the space from 19.5 up to 20.5. So if we want all of the 20 bar and everything less than it, we've got to go not up to 20, but up to 20.5. Okay, because going all the way up to 20.5 will ensure that we capture all of the 20 bar, which goes from 90.5 up to 20.5. So what that means is that to approximate this, that is going to be approximately equal to the probability that y, our new normal distribution, is less than or equal to, or less, I remember it doesn't matter with normals, is less than 20.5. So you can see it really does matter with binomials, because less than 20 just wouldn't include that bar at all. But since it's less than or equal to 20, it does. And since it includes that bar, we need to go all the way up to 20.5. One way that I do this, I don't want to be drawing out bars all the time, is I write out some numbers that are around my, my target number, which is 20. And I say, well, if I want everything which is less than or equal to 20, I kind of scoop up all the things which are less than or equal to 20. And what I can see is, where have I cut through? I've cut through at 20.5, and that tells me where my cutoff point is for the normal distribution. Imagine that it had said probability that x is less than 20. Well, then I'd be scooping up everything that's less than 20, and then I would have cut through at 19.5. So you can kind of work it out that way. This technique that we've done here is this whole thing here where we bump it up or down 0.5 is called a continuity correction. So continuity correction, and probably the most common reason for going wrong in these questions is just not doing it. And if you don't do it, it goes wrong, right? It gives you a bad approximation. So you must include your continuity correction whenever you move from a discrete, which is binomial, to a normal, which is continuous. So it's that move from discrete binomials to continuous normals. That means you have to do a continuity correction. Okay, let's get some more room. Now all we need to do is solve this, and we solve it in the normal way. No pun intended. So we've got our distribution with a mean of 27. And we want the probability of being less than 20.5. So that's, let's say, here. So we want this probability here, and we want the z value associated with 20.5. So we're going to find that using our standard formula. So it is the x value, 20.5, minus the mean, which is 27, divided by the standard deviation. And be careful, 14.85 is the variance. So it's the square root of 14.85. Now that's minus 1.6867. So that's the z value here. And now I can just use either tables or the calculator to solve this. So I'm just going to use the calculators. The probability that z is less than minus 1.6867. Well, let's just go to menu and the normal CD. Lower, well, it's unbounded on the lower end, so that. And then minus 1.6867. Standard deviation of 1. Mean of 0. And there's our answer, 0.0458. And so that is how we do a normal approximation to a binomial distribution. In the next video, we'll just look at a few more examples, so I'll see you there.